here with Axel, Anna-Marie, and Caliber of Siemens, and we're talking about orchestration. So,
in one sentence, what is the industrial AI orchestration layer for a plant team?
So to me, in one sentence, it's the ability to safely activate AI for production systems. What is it for you?
For me, the orchestration layer is the system that facilitates the relationship between higher order AI models and the operators on the ground and the control system, those three entities.
For me, it just makes AI work for our customers. And that's the glue in between.
When the plant is drifting, does orchestration step back or step in more? And how do you decide?
Yes, so actually that is exactly the point, that when we see data drifts, right, and we see constant changes in the environment, then we constantly want to not only monitor them, but also see, okay, now what do we have to change, right? What do we have to do differently? What kind of parameters do we have to adjust? And then this is where we want to adjust them safely and validate them against simulations before we actually write back into the control system and actually go ahead and adjust the parameter.
And I have a question for you. When you say the plant is drifting, are you referring to data drift or process drift, or what are you referring to when you're asking that question?
That's a good question, on a data drift as
Okay,
well.
data drift, okay. So in my mind, the orchestration layer itself is not so much about data drift, it is about process drift, okay? Because data drift is a different problem that you would handle a different way. Process drift, to me, is the actual key thing that we're addressing here, which is that the physical process is drifting. If the data is drifting from what the physical process would want, I would handle that one way. If the actual physical process is drifting, I would handle that another way. So it's kind of, but the orchestration layer itself is really about like I said, the orchestration of the process and the people that are associated with the process, and then any AI models associated with that. There are other systems that deal with data drift.
In batch and multi-product plants, are you targeting steady-state optimization first, or the risky transitions like startups, shutdowns, and grade changes?
I would say obviously the steady-state optimization is the first use case. Generally speaking, the implementation of this thing is more, it's the reason why you do it is the same across, which is safety at the end of the day, but the use case, like steady-state optimization versus startups and shutdowns, is more a per customer basis. So what's the customer's outcome? Because the system is designed to handle really the orchestration of all these entities, and so it's almost more about a policy thing than it is a technology thing as to how I'll say what things you do with it, if that makes sense.
Can I add something?
Absolutely.
The steady state production was the optimum for many, many years. If I look at the challenges that we see in the process industry today, you have to deal with different feedstocks. You have to deal at a certain point of time of the day with different energies, because you may want to use green energy when available. You may want to reduce your production. Giving an example, for hydrogen, if you don't have green energy available, you want to produce green hydrogen, so you may want to decrease your production. You still want to stay in the boundaries. So the steady state does not happen that often anymore. And this is where the optimization, not only from an unwanted drift in the process, becomes much more often something that you need to handle. And I think this is exactly where the orchestration technology can help our customers to optimize their production and make it more autonomous.
Process people don't need a perfect twin. What makes a simulation good enough to trust for operational decisions? And what decisions would you never base on simulation alone?
So first of all, when we say simulation's good enough, the measurement that I generally use is that I will compare the output of a simulation and the output of the real production data. So first of all, you have to have alignment in terms of how you measure it, right? So you need to make sure that the simulation is no higher fidelity than the actual data acquisition on the floor, right? Because if it is, I've seen this all the time. where they capture the data in this really, really expensive way, and then they train the simulation on that high fidelity, and then the simulation doesn't line up to what's real, simply because they didn't actually capture and measure it using the same methodology, right? So from my perspective, what makes it good enough is that you could have a senior operator actually compare the outputs of the simulation to the outputs of a day of operation in the facility, and if perturbing the simulation in the same way that the perturbations occurred in the facility, to me, aligning those two things well enough is what would make a simulation good enough.
And what we probably would never compromise on is safety. So if we have safety functionalities that are built up in parallel in a separate safety system, we keep it in a separate safety system. Mm-hmm. And the safety system will override whatever we do manually or whatever we do out of a simulation or an optimization. This is what safety is for.
And maybe also just to add this other adjacent thought that I shared earlier, right? Because there's often this fear that now we have to create from scratch a lot of new simulation tools to safeguard our AI or our decisions. And I think I would always encourage operations teams to look back into all the great simulations that have already been done at engineering time. Yes. And then, yes, of course, compare the fidelity and the abstraction level that we actually require in operations versus in engineering. But I think generally like the reuse of simulations that have been done at engineering time, maybe also things that have been done in virtual commissioning, which has been a technology that's been around now for more than a decade, and really making these kind of simulations, these digital twins, executable at runtime in operations is a great opportunity for reuse. So yes, there is integration effort and there is the need to build simulations or to actually check whether simulations are at the right granularity level that we need, but we likely, or what we see most often, is we don't need to build them from scratch.
If orchestration recommends an action, but the operator disagrees, who has the final call? And how do you protect operator ownership while improving performance?
Well, I mean, the first step is the simulation and the optimization is proposing a change of operation and is making very clear why it's needed. But the final call is with the operator. Acknowledge it, take it over or don't. So this is the way we can start doing it, and then if we feel very comfortable, we may at a later point of time go into complete autonomous operation.
So the operator always has the ability to override and always has the last call, and really what's critical, like Axel just said, is that explainability for the operator to also understand where did this recommendation come from, and maybe also give reasons or feedback as to why they chose to override or why they chose to accept it, because that's going to enable us long term to eventually then design some of the processes completely autonomous.
And I'll say that there's an inherent assumption to your question that's actually really interesting. The truth is that in most times that I've seen someone try to implement AI in an unguarded way for the control system, what they've failed to do is actually create the bindings that actually tell, does the operator know an AI model is running? They don't know. So many companies, in fact, the vast majority of things that we have seen when people just try to do it, is they don't actually have a signal that exists in the system that says an operator is in control. This thing got put into manual mode, all the AI models have to shut down. Well, this is why we talk about module type package, because these state machines in part 4 of the standard, by the way, the state machines that are present in part 4 of the standard says there is an inherent order of authority. And the order of authority goes, operator has order of authority. Then after that is any automated actions that come from the system internally. And then after that are any operations that come from the automation system externally to the system, right? Those external things, which are the commands that come from the orchestration layer itself, those are the only time an AI model should be running is when the mode of the system is an automated external. If the operator has it under control, the operator has it in control. And this is the inherent thing, is that people don't think about this at all.
But the challenge that we really come from is, if I look back 10 years ago, at least 50% of all the control loops were manual. because the advanced process control was not good enough. They never reached a steady state. The feedstock was not stable enough. The production requirements or preconditions were not stable enough. Now the challenge to all of our customers are the environment situation with requirements on sustainability, cost of energy and feedstock, the availability of feedstock and energy has changed. At the same point of time, a lot of those operators, very experienced operators, are going to retire. We're going to see the baby boomers to leave our operations latest by 2030. So we better prepare to run the operations in a more complex environment with less people. And this is exactly where we can help.
Thank you all for your insights, and if you have questions, feel free to leverage the hashtag on the screen.